According to the National Electrical Code, specifically Section 310.15b7, which covers conductors, and more precisely, the neutral conductor, and alternating current electrical systems, the ampacity of the neutral conductor must adhere to the requirements outlined in 310.15b7. Now, focusing on subsection D, it addresses feeders supplying a panel board with 100% neutral load imbalance. If the calculated neutral current exceeds the calculated current for the ungrounded conductors, then the neutral conductor's ampacity must be no less than that of the ungrounded conductors. In simpler terms, if the neutral is carrying more current than the hot wires, it needs to be the same size or larger to handle the load safely. The NEC also touches on this in section 220.82, which deals with the size of the neutral conductor. It states that the size of the neutral conductor must comply with both 310.15b4 and 310.15b7 as applicable. Essentially, both sections work together to ensure that the neutral conductor is appropriately sized for the expected load. So, to directly answer the question, no, you cannot reduce the size of the neutral conductor in a subfed panel based solely on the assumption that there will be a significant neutral load. The code requires a proper calculation to determine the necessary ampacity of the neutral conductor. According to NEC sections 310.15b7 and 220.82, the neutral conductor must have an ampacity not less than the ampacity of the ungrounded conductors if the calculated neutral current is greater. This means you need to perform a load calculation to determine the expected neutral current before deciding on the neutral conductor size. Reducing the neutral conductor size without proper calculation can lead to overheating, voltage drop, and potentially hazardous conditions. The code prioritizes safety and requires that the neutral conductor be sized appropriately to handle the anticipated load. In summary, always perform a load calculation to determine the required neutral conductor size based on the specific installation requirements and the expected neutral current. Never assume a reduced neutral load without verifying it through calculations as outlined in the NEC. Remember that the National Electrical Code is a comprehensive set of standards designed to ensure electrical safety. It's crucial to adhere to these standards to protect people and property from electrical hazards. Always consult the latest edition of the NEC and seek guidance from a qualified electrician when working with electrical systems. When dealing with electrical installations, especially concerning conductor sizing, it's crucial to understand the underlying principles and the specific requirements outlined in the National Electrical Code. Let's delve deeper into the key aspects of NEC sections 310.15b7 and 220.82, focusing on the practical implications and calculations involved in determining the appropriate neutral conductor size. Firstly, it's important to define what we mean by subfed panel. A subfed panel, also known as a subpanel, is an electrical panel that receives its power from another electrical panel, typically the main service panel. This arrangement is common in residential, commercial, and industrial settings where multiple distribution points are needed. Now, let's break down NEC section 310.15b7 in more detail. This section provides specific guidelines for determining the ampacity of the neutral conductor in alternating current electrical systems. Ampacity, as a reminder, is the current carrying capacity of a conductor expressed in amps. Subsection F through F of 310.15b7 outlines various scenarios and conditions that affect the required neutral conductor ampacity. As previously stated, subsection D is particularly relevant to the question at hand, as it addresses feeders supplying a panel board with 100% neutral load imbalance. A neutral load imbalance occurs when the current flowing through the neutral conductor is not evenly distributed among the phase conductors. This can happen in various situations, such as when a panel board primarily serves single-phase loads or when there's an uneven distribution of three-phase loads. In such cases, the neutral conductor can carry a significant amount of current, potentially exceeding the current carried by the ungrounded conductors. The code mandates that if the calculated neutral current is greater than that calculated for the ungrounded conductors, the neutral conductor must have an ampacity no less than the ampacity of the ungrounded conductors. This requirement is in place to prevent overheating and ensure the safe operation of the electrical system. Now let's consider NEC section 220.82, which directly addresses the size of the neutral conductor. This section emphasizes that the neutral conductor size must comply with both 310.15b4 and 310.15b7 as applicable. This means that in addition to the specific requirements outlined in 310.15b7, the neutral conductor must also meet the general requirements for conductor sizing as specified in 310.15b4. To determine the appropriate neutral conductor size, a load calculation must be performed. This calculation involves assessing the expected loads on the panel board and determining the maximum neutral current that could flow under various operating conditions. The load calculation should take into account factors such as the type of loads, the number of circuits, and the anticipated usage patterns. Once the maximum neutral current is determined, the appropriate conductor size can be selected based on its ampacity rating. It's important to consult the NEC tables and ampacity charts to ensure that the chosen conductor has sufficient ampacity for the calculated load. Now, let's discuss some practical examples to illustrate how these principles apply in real-world scenarios. Imagine a sub-fed panel board that primarily sells lighting circuits and receptacle outlets. In this case, the neutral load imbalance could be significant, as most of these loads are single-phase. If the calculated neutral current exceeds the current carried by the ungrounded conductors, the neutral conductor must be sized accordingly. On the other hand, consider a sub-fed panel board that primarily serves three-phase motors. In this case, the neutral load imbalance may be minimal, as the three-phase loads tend to be balanced. However, it's still essential to perform a load calculation to verify the neutral current and ensure that the neutral conductor is adequately sized. It's crucial to remember that the assumption of a reduced neutral load without proper calculation is not permitted by the NEC. The code requires a thorough assessment of the expected loads and a determination of the maximum neutral current before deciding on the neutral conductor size. Reducing the neutral conductor size without proper justification can lead to several problems, including overheating, voltage drop, and potentially hazardous conditions. Overheating can damage the conductor insulation, leading to short circuits and fires. Voltage drop can cause equipment malfunction and reduce performance. In extreme cases, undersized neutral conductors can create a shock hazard. Therefore, it's essential to prioritize safety and adhere to the NEC requirements for neutral conductor sizing. Always consult the latest edition of the NEC NSEET guidance from a qualified electrician when working with electrical systems. In conclusion, the sizing of neutral conductors in sub-fed panels is governed by NEC sections 310.15b7 and 220.82. The code requires a load calculation to determine the maximum neutral current and mandates that the neutral conductor have an ampacity no less than the ampacity of the ungrounded conductors if the calculated neutral current is greater. Never assume a reduced neutral load without verifying it through calculations, and always prioritize safety when working with electrical systems. Let's further elaborate on the specific calculations involved in determining the neutral conductor size and address some common misconceptions. The first step in determining the neutral conductor size is to perform a load calculation for the sub-fed panel. This involves identifying all the loads connected to the panel and estimating their current draw. Loads can be broadly categorized as either linear or non-linear. Linear loads, such as incandescent lights and resistive heaters, draw current in a sinusoidal waveform. Nonlinear loads, such as electronic devices with switching power supplies, draw current in a non-sinusoidal waveform. Nonlinear loads can generate harmonic currents which can significantly increase the neutral current. Once all the loads have been identified and their current draw estimated, the next step is to determine the maximum neutral current. This can be done using various methods depending on the type of loads and the available information. For linear loads, the neutral current can be calculated by vectorially summing the currents in the phase conductors. For a balanced three-phase system, the neutral current is zero. However, in an unbalanced system, the neutral current can be significant. For nonlinear loads, the neutral current can be significantly higher than the current in the phase conductors due to the presence of harmonic currents. In some cases, the neutral current can be as high as 1.732 times the phase current. To accurately determine the neutral current for nonlinear loads, it's necessary to use specialized equipment, such as a harmonic analyzer. Once the maximum neutral current has been determined, the appropriate conductor size can be selected based on its ampacity rating. The ampacity rating of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. The ampacity rating of a conductor depends on several factors, including its size, insulation type, and insulation method. The NEC provides tables that list the ampacity ratings of various conductors under different conditions. It's crucial to consult these tables to ensure that the chosen conductor has sufficient ampacity for the calculated load. In addition to the ampacity rating, it's also important to consider the voltage drop in the conductor. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment malfunction and reduce performance. The NEC recommends limiting the voltage drop in feeders and branch circuits to a certain percentage of the source voltage. To minimize voltage drop, it's necessary to use conductors with a larger cross-sectional area. Now let's address some common misconceptions about neutral conductor sizing. One common misconception is that the neutral conductor can always be smaller than the phase conductors. This is not true, as the NEC requires the neutral conductor to have an ampacity no less than the ampacity of the ungrounded conductors if the calculated neutral current is greater. Another misconception is that the neutral conductor only carries the unbalanced current. This is also not true, as the neutral conductor can also carry harmonic currents generated by nonlinear loads. A third misconception is that the neutral conductor does not need to be protected by an overcurrent device. This is not true in all cases, as the NEC requires the neutral conductor to be protected by an overcurrent device in certain situations, such as when it's part of a multi-wire branch circuit. In summary, determining the neutral conductor size requires a thorough load calculation, consideration of harmonic currents, and adherence to the NEC requirements for ampacity rating and voltage drop. It's crucial to avoid common misconceptions and always prioritize safety when working with electrical systems. Always consult the latest edition of the NEC and seek guidance from a qualified electrician when working with electrical systems. Let's delve even deeper into the specific scenarios outlined in NEC section 310.15b7 and discuss how they impact the neutral conductor sizing. This section provides a detailed framework for determining the appropriate ampacity of the neutral conductor, taking into account various factors such as load characteristics, system configuration, and harmonic content. Subsection of 310.15b7 addresses situations where the major portion of the load consists of nonlinear loads. Nonlinear loads, as previously mentioned, are electronic devices that draw current in a non-sinusoidal waveform, generating harmonic currents. These harmonic currents can significantly increase the neutral current, potentially exceeding the current carried by the phase conductors. When the major portion of the load consists of nonlinear loads, the neutral conductor must be sized to carry the maximum neutral current determined by a qualified electrical engineer or designer. This typically involves using a neutral conductor with an ampacity equal to or greater than the ampacity of the phase conductors. Subsection B of 310.15b7 addresses situations where the neutral conductor carries only the unbalanced current from single-phase 2-wire and 3-wire circuits. In this case, the neutral conductor can be sized smaller than the phase conductors, but it must still have sufficient ampacity to carry the maximum unbalanced current. The unbalanced current is the difference between the currents in the phase conductors. To determine the maximum unbalanced current, a load calculation must be performed, taking into account the anticipated loads on each circuit. Subsection C of 310.15b7 addresses situations where the neutral conductor is used in a 3-wire circuit derived from a 2-phase system. In this case, the neutral conductor must have an ampacity equal to or greater than the ampacity of the ungrounded conductors. This is because the neutral conductor in a 2-phase system carries the full current of both phases. Subsection D of 310.15b7, as we've discussed, addresses feeders supplying a panel board with 100% neutral load imbalance. This is a critical scenario where the calculated neutral current is greater than that calculated for the ungrounded conductors, mandating a neutral conductor ampacity no less than that of the ungrounded conductors. Subsection E and F address other specific situations and provide additional guidance on neutral conductor sizing. In addition to the specific requirements outlined in 310.15b7, it's also important to consider the general requirements for conductor sizing as specified in 310.15b4. This section provides guidelines for determining the ampacity of conductors based on their size, insulation type, and installation method. It also addresses factors such as ambient temperature correction and conductor dating. To ensure compliance with the NEC, it is essential to perform a thorough load calculation, consider all applicable factors, and consult the latest edition of the code. Remember that the NEC is a dynamic document that is updated regularly to reflect changes in technology and industry practices. Always use the most current version of the code to ensure that your electrical installations are safe and compliant. In conclusion, the sizing of neutral conductors is a complex topic that requires careful consideration of various factors. NEC Section 310.15b7 provides a detailed framework for determining the appropriate ampacity of the neutral conductor, taking into account load characteristics, system configuration, and harmonic content. By following the guidelines outlined in the NEC and consulting with a qualified electrician, you can ensure that your electrical installations are safe and compliant.